Graph the polynomial function. Our function f of x is a fourth degree polynomial function, and the first thing that we're going to do is find the power function that f resembles at infinitely large values of x. And that power function is going to be simply the leading term, which in this case is 2x to the fourth power. So y is equal to 2x to the fourth is the graph that our function f will eventually start to look like out at the tails, or at large values of x. 2x to the fourth power is a very steep and somewhat boxy around the origin graph that's opening up, and the end behavior for our graph f is going to have opening up to the right and up to the left tails resembling the end behavior of this power function. Now, in order to find the zeros of the polynomial, it's best to write our polynomial in the factored form. So our task is to factor this fourth degree polynomial. This polynomial has 4 terms, and it actually factors by grouping. We notice that if we group the first 2 terms together, they have a common factor of 2x to the third power. When I pull 2x to the third out of this first term, we're left with just positive x, and when we pull 2x to the third out of this second term, we're left with plus 6, and then we'll close that quantity. Now the value that's common out of the second group is minus 8x. We pull the negative out as well because we want to generate the same binomial from the second group as we did from the first group. So we need to pull that negative out in order to make that happen. When we factor negative 8x out of the first term, we have positive x that remains. And when we factor negative 8x out of the second term, we have positive 6 that remains. And now we can see that we do have the same binomial remaining out of both of these groups. So since both groups have the same factor, we can factor it out to get x plus 6 times the 2x cubed is what remains out of that first cluster, and negative 8x is what remains out of that second group. Now this factor is linear, so it's done. It doesn't factor anymore, but this factor does have a common factor again of 2x. So we'll copy paste the left-hand side and the x plus 6. We're going to pull out the 2x here, and what remains is now going to be x squared minus 4. In order to make this as clear as possible, I'm actually going to pull this 2x factor all the way to the front of our polynomial. So it'll be 2x times x plus 6 times x squared minus 4, which still factors more. This is the difference of squares. So our final factorization is going to be 2 times x on the front times x plus 6 times x squared minus 4 factors into x plus 2 times x minus 2. And now this polynomial has been completely factored. When the polynomial is completely factored, it's much easier to see what the zeros are going to be. The x value that causes this first factor to be 0 is x is equal to 0. Evaluating this function at 0 would cause the output to be 0, which makes this a 0 of the polynomial. If we evaluated the function at x is equal to negative 6, it would zero out this factor and make the entire product have an output of 0, so x is equal to negative 6 is a 0 of the polynomial. If we evaluated the function at negative 2, negative 2 plugged in for x zeroes out this factor and makes the entire product equal to 0. So x is equal to negative 2 is a 0 of the polynomial. And finally, if we evaluate the function at x is equal to positive 2, it zeroes out this factor and therefore zeroes out the entire product. So x is equal to positive 2 is also a 0 of the polynomial. Now all of the powers on all of these factors are positive 1, so each of these has a multiplicity of positive 1, and we can turn these into x-intercepts just by making the zeros into ordered pairs. And since the multiplicity of each of the zeros is odd, we're going to be crossing at every single x-intercept. And now it's time to find the y-intercept. The y-intercept is determined by plugging 0 in for x, and as we saw a moment ago, when we plug 0 in for x, it zeroes out this factor and therefore the whole product. So the y-intercept for this graph is the origin 0, 0, and now it's time to sketch our graph. Let's start by plotting our x-intercepts. We have 0, 0, negative 6, 0, negative 2, 0, and positive 2, 0. From before, we remember that we had an end behavior up, up, So we'll start up here in the second quadrant. We'll come pretty steeply down and through this first x-intercept. And when we get over to our graphing calculator, we'll see that we come pretty far down here with our relative minimum. Then we'll come back up to the x-axis, and this next x-intercept, we're going to pass through it, again because it has an odd multiplicity. We'll turn around in a smooth and continuous way and pass through our next x-intercept at the origin. We'll turn around in a smooth and continuous way and pass through our last x-intercept at 2, 0, and then finish up in the first quadrant within behavior that is up and to the left and up and to the right. Now we're being asked to find the relative maximum and the relative minimum values. We have 2 relative minimums on this graph and 1 relative maximum on the graph, and we are going to need to use our calculator to find these values. So in our calculator, we'll come over to y equals and we'll input the beginning equation. Best practice is to input the equation from the very beginning in case we made a mistake when we factored it. So we have 2x to the 4th plus 12x cubed minus 8x squared minus 48x. And we really can't see much of our graph from the standard viewing window. So let's go over to Window and use the boundaries that are recommended here on this image. So that looks like -10 to 10 on the x-axis with a scale of 1 is fine. On the y-axis, we're down below -200. Let's say -250 with a y maximum of 150. And let's make the scale 50 so that we don't have so many tick marks on the y-axis. And now we need to calculate the relative minimums and the relative maximum. All of those functions are found under Second Calculate. So we hit the second button and then access the calculate function. Let's start with the minimums. So we hit number 3. We just selected left bound on this minimum. Let's now go to the right and give a right bound and come back for the guess. So our first relative minimum occurs at 1.21 as an x-coordinate and -44.25 as the y-coordinate. Let's go ahead and get the other minimum. So again, we'll select the number 3 function here. So now we need to come all the way to the left of this second relative minimum and hit enter. We're asked for the right boundary for that minimum, so we come to the right of it, hit enter again, and then we are to put our cursor pretty close to the minimum itself for a guess. And the calculator is telling us that this minimum occurs at -4.65 with a y-coordinate of -221.25. Now we'll go second calculate one more time to get this time the maximum. So we select number 4. We move our cursor to the left of the maximum that we're looking for, hit enter. Move our cursor to the right of the maximum that we're looking for, hit enter again. And then bring our cursor back to kind of a guess. And this maximum occurs at -1.06 and 30.12. So let's answer our questions. We're going to find the maximum value, the relative maximum, and that relative maximum occurs at 30.12, the y-coordinate of the ordered pair. And then there are 2 minimum values, 2 relative minimums. One of them is the y value of this lowest ordered pair, -221.25, and the other relative minimum, which is the y value of this ordered pair, is going to be -44.25. Now where is the graph increasing? The graph is increasing in this interval and in this interval. The increasing interval starts with the x-coordinate -4.65 and ends at the x value -1.06. And then it starts increasing again starting at 1.21. So we use the union symbol, open up a bracket, 1.21, and it's going to be increasing from that point out to x is equal to +infinity. Now to determine where the graph is decreasing, we see that we're decreasing on this interval and in here as well. So we say our polynomial is decreasing starting out at -infinity. It decreases up to the x value -4.65. We use a bracket to close up that interval. Union. The polynomial begins to decrease again, starting at x is equal to -1.06, and it decreases all the way to the x value, 1.21. We close that up with a bracket, and these are our final answers for where the graph is increasing and decreasing.